All right, so this is Physics 1B for October 26th. We're nearing the end of the semester. We have about 6 weeks left or so. And today we're going to be talking about the first law of thermodynamics, um, what it is and how it applies to systems. And here's a set of topics that we're going to discuss. We're mostly going to be talking about, like I said, gases, the work that they do when their volume changes, such as like when a piston moves, and then some additional other topics that'll become probably more clear what those terms mean when we get to them. So we're going to start off by talking about one thing. Oh, the cord on my Wacom is like exposed. That's really bad. Hope this still works okay. Oh, that's really unfortunate. I'll have to order a new one. Okay, so the thing I'm going to start off by kind of talking about is what is a system? So the first law of thermodynamics is really about energy. And when we talk about systems, you may think about maybe mechanics. In mechanics, we would talk about, a system of objects. It could be like a box sitting on a table. And we describe the way in which work could be done on the object. Just let's look at a really simple example. If I've got a surface and then on that surface I have a box, then the system may consist of something like the box plus the earth or something like this. And let's add a ramp in here. So let's say there's a ramp here. So the system could be something like the box and the earth could be the system. And then we would describe any kind of energy changes associated with the box and the earth system. We would call energy changes, such as if the box were to move from here up to here, it would gain potential energy, right? But we could also talk about how that's done. If there's a force that's pulling on this box, so if someone pulls on the box in this direction with some kind of a force, then we'd say that force does work on the box, right? It does work on the box earth system. And then what happens to the energy of the system if this force does positive work, for example? What happens to the energy? So if the force does work on the box and it causes the box to be pulled up a ramp, what happens to the energy of the system? It gains energy. What kind of energy does it gain? It gains potential energy. Could it possibly gain any other type of energy? It could gain kinetic energy. So I'd have to tell you something about the way in which this motion occurred, right? I'd have to tell you let's say for example that this is done and maybe the velocity is held constant, right? So maybe in the process, maybe the velocity is a constant, okay? In that case, the work done on the system would be greater than zero, and also the change in the potential energy due to gravity would also be not equal, but would also be greater than zero, right? And if it's done at constant velocity, that would explain everything, right? And we could make the statement that the work done on the system would be equal to the change in potential energy due to gravity, right? Except there could be some other considerations here that I left out. This might be true as long as the surface is frictionless. But if we add friction to the equation, then the work done here would have to be the work done by the force. And then depending on how you think of friction, it's going to be a negative force, right? But it's going to be a negative work, but so I'll just leave it as a plus number, but this would definitely be a negative number here, right? Yeah, but in general, the work that's done on the system would lead to a change in the energy associated with the gravitational field, right? Assuming the velocity was constant. And if the velocity wasn't constant, like if the velocity increased as it went from this position to this position here, so if it was moving with some velocity at this point and then it's moving with some velocity here, we'd have to add into this the change in kinetic energy too, right? Okay, but the system in this case is the box plus the Earth. And why do I have to include the Earth? Why do I have to make the statement that it also includes the Earth? The force of gravity is acting on the box. Yeah, that's right. There's a force of gravity, and that force of gravity is like an interaction force, right? If I were to, for example, take this same experiment of like pulling an object up a ramp, and I were to place it like on a spaceship, for example, so if I have a really big spaceship that's traveling through space, and let's say that it's just coasting through space, so it's moving along with a constant velocity, constant, and then I perform my exact same, experiment. First of all, it's going to be very difficult to get the object to attach to the table without using like magnets or something like this, right? And all of a sudden, your system would just be, if I place the same system inside of here, I try to put a box on top of a surface. So first of all, it's going to have a hard time sticking to the surface. You're going to have to like push it and like make it sit there for a long period of time. And then if you exert any type of a force on the object, it's probably going to fly off the surface. So having the Earth there actually matters in this case, and it has an interaction force. And I'm mentioning this because this is going to matter for gases when we talk about gases. And I'm also mentioning this just to reorient you to understand the idea of what a system is. Okay. So let's think about now what we mean by a thermodynamic system. So a thermodynamic system is going to be some type of a closed system. And we'll say that this system has the potential to exchange heat with its surroundings. So it can do two things. It can basically exchange heat with, and it can do work on okay, that's what we would call a thermodynamic system, is a closed system that could exchange heat with and do work on its surroundings. Okay, I'll just give you like some simple examples of these things. So let's say that I have a gas in a container. So I have some kind of gas inside of here. And let's say that this container has some type of a piston, okay? And then underneath this, I put some type of heat. I add heat to the system by burning something down here, okay? So we add heat. And let's say that this piston that's up here is free to move up and down, okay? So what's going to happen to the gas as we add heat into it? What's going to happen to the piston? Is it going to go up or down? It's going to expand, right? So if we let some time pass, then what's going to happen to our system is that the gas is going to cause the piston to move up. So the piston's going to go this way. And that little difference right there is going to mean that the piston has moved up. The gas is still inside of here. and maybe we're still adding heat with the potential of that piston continually moving up. The more heat we add, the more the piston moves up. Okay, so what we would say is we added heat, and as a result, the piston moves up. Which means that it does work on its surroundings. Whoops. All right, so now the system in this case would be the gas itself that's contained within this container. And then the piston is kind of like its surroundings in a way, right? By moving that piston up, we could imagine that it could lift something, for example. Right? Like if we attach the piston to some weight, right? Like it could be something like, I don't need to draw this, but suppose that we've got our piston right here. And how would we do this? How do we make it lift something? You have to have some kind of a pulley or something like this. And maybe attach a string between the two of them. And then hang a weight right here or something like this. I don't know if this picture works exactly because I'm kind of just like drawing this off the top of my head, but I think this works, right? That if the piston would go up, I guess the weight would go down, wouldn't it? How do you make the piston go up and make the weight go up? Okay, I didn't think this through before I do this very well. But the act of the piston moving up would certainly do work on its surroundings. Yeah, ignore this picture. This picture's bad. Don't try to understand what this is. The fact that the piston moves up, though, means that it's doing work on the piston, right? So the system in this case is the gas, and the surroundings would be the piston itself. Your question is, so a thermodynamic system is a system that when its temperature changes, the system also changes. That's, one example of something that a thermodynamic system can do. Yeah. Okay, so what I want to do now is does this make sense? That the system is basically the gas, and it's, in a way, its container, and then the surroundings are the piston? The fact that the piston can move means that work is being done. Okay, so let's define some of these quantities and talk about whether they're positive or negative. So when we add heat, we're going to use, for heat, we use the symbol Q to represent quantity of heat. And for work, we represent the symbol W, right? So if I have some system, if I have some system right here, and I add heat to it, so if heat comes in, then we're going to call the heat coming in as positive, okay? If, as a result of adding heat into the system does work on its surroundings, then we're going to say that work out is also positive. So when we add heat in, we're going to define the Q to be positive. And when work comes out of the system, which is what's happening here, like in this case, Q would be greater than 0 and W would be greater than 0. We're adding heat into the system, so the quantity of heat going in is positive. And it does work on its surroundings by moving the piston. So that's positive as well, okay? The opposite possibility could be that the system could give off heat in some way. Here, whoops, let's use the same color. So if the system gives off heat, we're going to call that negative. And if the environment does work on the system, then we're also going to call that negative. So this would represent the environment or the surroundings. And maybe by the environment doing work on the surroundings, that could cause the heat to go out of the system. You can have situations in which, Q is positive, but W is negative. We'll talk about how that can occur later. So when work comes out of the system, this would be like what we just talked about a second ago. This would be like an expanding gas. And when work goes into the system, this would be like a gas being compressed. Okay, these two don't have to be connected to each other, but just in general, I'm kind of trying to define, if I have a system, if heat comes in, we're going to define that as positive. If heat goes out of the system, we're going to define that as negative. This would be, what's an example of heat coming out of a system? You could have like a cup of coffee that's hot, okay? So you could have like a cup of some beverage that's like steaming hot or something like that, right? This would be an example of heat coming out of a system, right? If you touch the cup, you're going to feel heat come out of it, right? Okay, these are basically just sign conventions. I'm just setting this up so we all know what I mean by Q positive, W positive, Q negative, W negative. Do these sign conventions make sense to you all? Any questions? Okay, so, all right. We're going to start off with the first line here then. We're going to talk about work done during a volume change. This is basically what we're going to be talking about for all of today's class, is just different processes in which heat comes into a system or heat goes out of a system, and we'll talk about work being done on them, and we're going to connect all of this to internal energy, temperature, pressure, and volume for gases. And we'll talk about how it works for ideal gases and for non-ideal gases. That's kind of the goal today, is to describe all those types of processes. And really, I mean, just in general, if you want to think about a bigger question, we'd really like to understand today, to some extent, what's going on inside of, like, the combustion engine inside of your car, right? Or what's happening when power is being generated at a power facility or something like this. What are the kind of energy exchange processes that are occurring? Because remember that quantity of heat is measured in joules, and work is measured in joules as well, right? So really, this is all about energy, what we're talking about today. Okay, so let's talk about kind of the first major topic here, which is the work done during a volume change. So how much work is done when the volume of the system changes via expansion? All right, we're going to grab these two pictures here. And we're going to move this one over just a little bit so we have room to work. That might be too small where you can't actually read those letters. Okay, so in this case, we're going to have a system like the one that's drawn right here. And we're thinking about molecules within the system and what happens when one of the molecules hits this movable piston right here, okay? So we've got a container. It's got gas molecules in it. The gas molecules are hitting the piston and they're bouncing off of it. What this picture here is showing is, in one case, when the piston moves away from the molecule during the collision, so the piston's moving to the right, then the velocity of the molecule before and after is going to be such that you've lost velocity. And as a result, the molecule loses kinetic energy and it does positive work on the piston. Okay? So this would be what would be happening in this situation, would the gas be expanding or compressing? What is this representing right here? Expansion of a gas or compression of a gas? Piston is moving to the right, and the molecules are losing energy. Yeah, this is the expansion of a gas, right? Okay. Just think about in your mind what that would mean. I mean, would it make sense that the molecules would be losing energy if it's expanding? Does that seem reasonable? On like a macroscopic scale? Without knowing anything else about it. Like, we're not saying anything about how temperature is being affected here, whether it's just freely expanding. I mean, maybe it's expanding because you're heating it up. I don't know. There's different possibilities. Okay, but the other thing is, it says the molecule loses kinetic energy. It does positive work on the piston, right? So this would be a situation where the work is being done on the surroundings, so the work is greater than 0, right? Okay. The other possibility would be that the piston's moving towards the molecule during the collision, right? So the piston's being compressed either by external forces, or maybe the gas is being cooled, and as a result, the piston is kind of, moving inwards due to the pressure getting less. Whatever the reason, this would be compression. And what's happening now is that the molecule's gaining kinetic energy. So in a way, the internal energy of the system is probably increasing, but the work here has to then be less than 0. Okay? So this is like work goes out of the system, and this is like work done on the system. Okay? When work is done on the system, we call the work negative. And when the work is done by the system, then we call it positive. Okay? All right. So what we want to do is we want to come up with a way to relate the work done to the pressure and the volume. All right? And so what we're going to do is we're going to use this picture right here. The idea is that you have a system, and you have a force that the system exerts on the piston. That force, we've learned, can be related to the pressure of our system. So P is the pressure of the system, multiplied by the cross-sectional area of the piston itself. Right? So P is the pressure. And then F would be the force that's exerted by the system on the piston. Right? So let's imagine that the force that's exerted by the system pushes the piston through some small distance dx. Then the amount of work that's done is equal to, well, in general, it would be the force exerted times the distance that the object moves. In this case, this work is positive because the force is in the same direction as the displacement. So we could say that dW then can be written as, we write the force now as, P times A times dx. But if we look at what A times dx represents, we have our system. It's closed on both ends, right? Which means it has a fixed volume. So, it could start off with some volume V. What does A times dx then represent? What would the cross-sectional area here multiplied by dx, what would that represent? It's volume, but if you think about it, like, this system has two states, right? It starts off with some initial volume here, and then it expands to here, so its volume changes, right? It went from some initial volume to some final volume. And I would say that, okay, we're just saying it's the volume at some point x. So its area, it's not multiplied by the total distance, right? it's multiplied by the change in distance, right? So we could say that it starts off with some initial x-coordinate and then it moves to some final x-coordinate, right? So its initial volume would be this, right? We could say like its initial volume would be the area times the initial distance, and its final volume would be the area times the final distance, right? So then what would a times dx represent? What does dx even mean? Yeah, it's the change in volume, right? So dx is basically x final minus x initial. So a times that. Oh, whoops, not sorry. This is dx. X final minus x initial is dx. So if I take a times that, that's what a times dx is. And this should be equal to the change in volume. So for change, we use the letter d, right? And then we put a v here. So what this represents then is that the work done by the gas on its surroundings should be equal to pressure times ADX, but ADX is just going to be the change in volume. So in general then, if I want to get a definitive, if I want to calculate, for example, the work done, I would need to integrate this expression from the initial volume to the final volume. And often using the symbols initial and final can get a little bit confusing with the processes we're going to talk about, because we're going to look at processes that might move from one volume to another, and then to a third, and then to a fourth, and then back around to the initial volume. Like we're going to talk about processes that are what we're going to call cyclical. So we'll just say V1 and V2 to represent the volume at state 1 and the volume at state 2. And to find the work done by the gas on its environment, we would just need to integrate like that. And this ends up being not a hard integral. It ends up being a pretty easy integral, because often, especially with like ideal gases, we can relate the pressure directly to the volume, right? So in the example, we'll do an example like that, like next. Okay, so this would represent the work done by the system. Now keep in mind that if the work done is positive, like if you calculate this and you get a positive number, then the work is done by the gas on the surroundings. But if you calculate this and you get a negative value, that means that the surroundings are doing work on the system, such as when a gas compresses, for example, right? But that's how you do the calculation right there. The integral of PdV. Anyone have any questions? So let's look at, I think it's this picture right here. So let's consider what this means. An integral, right, represents an area under a curve, right? That's what when we say integral, there's always some function, and we're taking the area under that function. So in order to have a proper function here, we would need the pressure as a function of volume, or what we're going to call PV diagrams, okay? And what this explains is the work done, just as it says here, is equal to the area under the curve on the PV diagram, right? So here's a PV diagram, and here is a blue line that represents the path that we're taking, okay? The path is going to be very important in these processes. But here we have pressure versus volume. Now, why does it look like this? Well, probably because the person that made this was thinking about, the ideal gas law. Ideal gas law says PV equals to nRT, right? But if you divide the volume, then you're going to get an expression like this, which means you're going to get a curve that looks like 1 over x, right? A curve, 1 over x would be a curve that looks like this, right? So we're looking at some portion of that curve here, between 0.1 and 0.2. because pressure is going to be inversely proportional to volume. Yeah, and so there's three possibilities here. One would be the work done when we move from 1 to 2. So what's happening? What's happening in this picture right here? What does this represent? Is this a gas that's expanding as you go from 1 to 2, or a gas that's being compressed or contracting? It's gas expansion, right? How do you know? Because we assume volume is increasing to the right? This is probably positive volume axis, and this is probably the positive pressure axis. So as we move from point 1 to point 2, the volume of the gas goes up. As a result, the pressure of the gas went down, but because the volume expanded, we would assume that this gas pushed a piston in some way, right? It pushed the piston, so it must have done work on that piston. And as a result, when we look at the area under the curve between points 1 and 2, we get a positive value, right? Get a positive value. Okay, does that picture make sense to you? A gas expands, and as a result, its volume goes up, right? It started off as a small container with the piston here, and here, we'll make larger walls here. And then after some time, it moved to here. So this represents volume 1. This represents volume 2. And we could define what its pressure is with some type of a pressure gauge. And we know that volume 2 is greater than volume 1, but pressure 2 is less than pressure 1. Right? I realized that I was trying to figure out how we could think of this gas as doing work on the piston, and I forgot that the piston itself has weight, right? So just by lifting the piston by any distance at all, you've done work on the piston, right? I didn't realize that. But you still do work even if it was on its side, okay? So that's this system right here. This would be 1 to 2, area under the curve, positive, therefore work done on the system, right? Or sorry, work done on the environment by the system here, right? Because W is positive. Now, of course, we could think of the opposite happening. Someone could come along and they could exert a force down this way. This would be part B. If they exert a force down this way, it could cause the gas to compress from V1 down to V2, from here to here. Because in this path, we're going this way. I don't know if you can tell because it's kind of blurry there. We're going from 1 to 2. And when we go from 1 to 2, then basically all we've done is we basically flipped our what are these called? The endpoints of the integral. And when you flip the endpoints and go backwards, then you're just going to get the same integral with a negative sign. And I guess that the convention that they're using is that this cross-hatching here represents that the work is negative. But I hope you could see for yourself that if you move from this point to this point and do that integral, you're definitely going to get a negative answer, right? So in this case, work is done on the system by the environment, and the work is negative because the area under the curve is going to be negative in this case, right? Does that make sense? Okay. So work is negative here. Work is positive here. System does work on environment. Environment does work on system. One last possibility would be if the pressure is constant in this equation right here, you could just pull the pressure out and you get a much simpler relationship, which is just that the work done is going to be equal to constant pressure. You would just have V2 minus V1. So this would be the work done for a system when you have constant pressure. And just to throw a word out there that you're going to see later on, constant pressure is also called isobaric. Later on, we're going to talk about isobaric, isothermal, adiabatic, and all these different things that I feel like I learned about these things in chemistry as well. Do you guys talk about adiabatic processes in chemistry, or is that just physics? Maybe I'm wrong. Isobaric, isothermal. Are these things you talk about in chemistry? Chem as well? Okay, I thought so. All right. Yep, so if you have constant pressure, then of course the pressure line is going to be straight, and then the area under the curve just ends up being equal to the pressure multiplied by the difference between these points, i.e. the area of the rectangle. Of course, even at constant pressure, you could go from 2 to 1, and the work done could be less than 0. Right? Okay. Let me make sure that I don't want to... We're going to talk about paths. Okay. Oh, we can do this one. I thought there was one other thing we could do. Okay, let's just do this problem real quick. All right. So, isothermal expansion of an ideal gas. As an ideal gas undergoes isothermal or constant temperature expansion at temperature T, its volume changes from V1 to V2. How much work does the gas do? All right. So, constant temperature, moving between volumes. How can we make that happen? What will we need to do to increase the volume without the temperature decreasing? How can we do that? Decrease the pressure? Decrease the pressure. Yeah, maybe so. Oops. So what's our equation for an ideal gas? It's that pressure times volume is equal to nRT. How much work does the gas do? I think... Okay, I'm gonna draw something. You can tell me if this satisfies what's going on here or not. So let's say that I have a like a flimsy seal or something like this. I've got a container, and inside of it I have a gas, and that gas starts off with a volume that we call V1. Okay. And it's going to expand to a new volume. So we're going to have two containers here. So we're going to have a fixed, like, heavy weight on the top right here. And we're going to have a barrier right here. Okay. But this barrier, let's say that it's about to break. Okay. So the system starts off with a volume V1, and this one has a pressure P1, but this barrier is flimsy. Maybe it's made of Kleenex or something like this, and the pressure in here is high enough that it's going to expand. So the volume is eventually going to expand out to here. So we're going to end up with a volume V2, and we're going to have a pressure P2. So this is just going to break. Because I don't want I don't want the gas to have to do any work or anything like this. I believe this is called free expansion. Free expansion. And we're also going to say that the temperature is going to remain the same here. And I don't know if that's believable or not. Would you believe me if I said the temperature would probably stay the same in this case? Anyway, so you guys said decreased pressure. Let's see if that's what we have to do here. Okay, so we just learned that if I want to find... Okay, we're looking for, as an ideal gas undergoes isothermal constant temperature expansion at temperature T, its volume changes from V1 to V2, how much work does the gas do? All right, we just learned that work was equal to the integral of pressure with respect to volume. We know that the pressure is given by this expression, so we can write the pressure as just nRT divided by the volume. And it's moving from volume V1 to V2. So the work done now we can pull out the nRT, because the temperature itself is not changing in this process. And we're just going to be doing the integral of dV over V from V1 to V2. What's that integral going to be equal to? Natural log, yep. So we'll get nRT and the natural log of natural log of the volume. So we just end up getting nRT times the natural log of, it's going to be natural log V2 minus natural log V1, but you all probably know that that's also equal to the natural log of V2 divided by V1. And that would be equal to the work. Let's see, and I think as long as V2 over V1 is positive, then this should be positive, right? That makes me want to check something. As long as it's, let's see, 1 second. As long as it's greater than 1, right? It should work, right? Yeah, okay. Yeah, as long as V2 is V2 over V1 is positive. Not that just positive. V2 over V1 has to be greater than 1. Yeah, as long as V2 over V1 is greater than 1, then you're good. But if V2 is less than V1, it'll be negative, which is what you want, right? Yeah, okay. V2 over V1 has to be positive because of the natural log. Yeah, as long as V2 is greater than V1. But if V2 is less than V1, then it would be negative, right? Which is exactly what we want. We want, when the volume goes up, we want it, the work done to be, yeah. Yeah, I don't think this picture I drew is quite accurate for this, though, is it? Because I don't think this gas would do any work, other than the work it did to break this thing right here. I think you need to put a piston in here. I think the way that I should have drawn this... This is what's called free expansion, but I think I introduced it a little too soon. I think you do have to have some kind of fixed piston here for it to do work against. So you'd have to have your piston here, and then it would have to move up to here. Put a little handle on the piston. Yeah, sorry. That's, I think, a more consistent picture of what's going on here. I just wonder if it's okay that the temperature doesn't change from here to here. I think it is. That's fine with you guys, right? The temperature wouldn't change in this case? Anyone look at that and see, like, big alarm bells going off in their head that there's a problem? Looks okay to me. I think it's fine. I think it's fine. Okay. Okay, I guess this is a good place to stop for our break. What we'll talk about next is what's going to be called paths between states. And let me just see real quick here. Okay, yeah, that's for this next one. So that's what we'll talk about next, but let's take a break until 11:06. And I'll stop the recording.